Right. So let's see how to go ahead with working on with LT Spice. As I said, make sure that you have already downloaded this LT Spice from this website for the Windows. After doing that, you can just double click on the LT Spice. So you get a screen something like this. Now, before going on to this, I would like to make sure that few things need to be understood by you. Right. In order to construct a circuit or in order to simulate a circuit in a virtual platform, something like this, three things are important. First thing, construct a circuit. Say I'm constructing one amplifier. So you need to know what are the resistance, what are the resistant values, what are the input source, what are the active devices which I need to include, what are the passive devices I need to include, where are the places where I am going to take my output, and what type of output I am going to take. This clarity you need to have before you start your design or simulating your design. So first thing is about you finish the paperwork by calculating appropriate values of the component which you are using and list out what are the active and the passive components, what are your input sources, and what are the output you are expecting for, or where are you going to tap your output. This is the first step. Second step, you need to include the model files. What do you mean by model files? See, basically, a model file is a one which characterize that particular device. Say, for example, I am using a MOSFET. So generally, if you look at a MOSFET, say something like this. Let me go here. Let me start a new one. Let me show a MOSFET, something like this. Let's take this. This is a MOSFET. This is a symbol which I have kept here, and I claim that this is a MOSFET. But the reality is, it will never become a MOSFET until unless you characterize this symbol for some sort of characters. What is that? You would have read for a MOSFET. A MOSFET will work in the cutoff region, linear region, saturation region, all this. This region variation takes place based upon my input voltage, VGS, VDS, threshold voltage, all these ideas. So when I say the model for this particular NMOS, what I mean to say is the list of parameters which describes this MOSFET behavior under different voltage biasing conditions need to be kept as a file. And for that model file, I create a symbol, something like this. In fact, if you go with some other tool, this model, this NMOS symbol itself will be slightly different. So this symbol can be created by you, or even I can keep any other symbol created by me for that particular characteristics. But general by convention, we use this symbol for NMOS, and typically we are also using another one symbol without any break here. I believe you would have also seen that. So that could also be used as a symbol for a MOSFET. Or ultimately what I'm trying to say is a symbol is a one which has been assigned by me. It could be given any sort of symbol until unless you are not going to move away or deviate from the convention. That's it. So you create a symbol. For that symbol, I have a list of model characteristics or the behaviors of the device under different conditions, different voltage condition, different temperature condition, different biasing conditions. I give the set of characteristics. This characteristics file, I call that as a model file. Now, whenever I pick up this MOSFET symbol from my library and I am keeping it on the design window, actually what I'm trying to do is this MOSFET is going to attach itself to the library that should be available in my system. Say, for example, I am giving some voltage on my input to the gate of this particular MOSFET. and I would like to see what is the output across the drain and the source. So what I'm trying to do for this particular MOSFET, I am giving some voltage as my input source. This is typically same as doing this in a lab on a breadboard by inserting a 4-terminal MOSFET and giving an appropriate voltage between gate and the source and trying to see what is my output across the drain and the source. So there you kept a real MOSFET, but here I have kept a symbol of that MOSFET and attach its behavior as a model file. So one point what we need to understand is you first design the circuit, then make sure all the components which you use in the design has its own model files. Generally, if you look, the spice tools, something like this, they have the model file. Say something like this. I am using a 555 timer. Probably you would have seen the 555 timer would be something like a rectangular shape with appropriate pin numbers. I believe 5 plus 5, 10 number of pins. Then I simply use that symbol over here and give some appropriate voltage, and I'm thinking that this will act as a model. I mean, this will act as a 555 timer and you are expecting an output there. But remember, unless you don't have the corresponding model file for 555 timer in your library, this will not reflect the behavior of your 555 timer which you have used in your circuit. So the bottom line is you need to make sure that particular 555 timer is available in your login, or you need to make sure that from the company you can download that as a file, .lib file they used to call, .library, .lib file. This lib file need to be taken and included in our design. Is this point clear? So basically, if I want to work with some of the new devices, two things I need to get. One I call it as .lib file, one I call it as a symbol file. So .lib file corresponds to the model file of that particular device. Then symbol file corresponds to the symbol which is used to denote that particular device. So usually I can show you that these two files will be taken from different vendor. I may be working today, I may be working with the MOSFET of one model parameters. Tomorrow I would like to work with some other model files which has been manufactured by some other company. So I can get the model file and the symbol file from them and put it in my own library, and then I can use it. Right? That's all. So first thing, construct a circuit, make sure that the model files are attached. Third thing is doing analysis. When I mean I'm going to perform certain analysis, majorly you can do three type of analysis, right? Apart from that also you have few, but let me quote only the major three. The first one is transient analysis. Any analysis which has been done with reference to time. Say, I would like to measure the current that is flowing through this MOS device. So, the current that is flowing through this MOS device over a period of time of say 10 minutes. So, 10 minutes will be along your x-axis and the y-axis will be the current that is flowing. So, any parameter, or I would like to measure the voltage VDS between drain and the source along the time axis of 10 minutes or 15 minutes. So you are trying to draw or sketch out a graph between two parameter. One can be the current or voltage, the other one x-axis is my time. This type of analysis is called transient analysis, or any analysis which is being done with reference to time is called transient analysis. The second analysis is The second analysis is the DC analysis. In order to do the DC analysis, what I'm trying to do is I try to keep all my parameters, DC voltage, DC DC current, and I'm trying to measure the output DC voltage or DC current. Say I'm giving VGS, my DC input voltage, and I'm measuring VDS, my output voltage, DC voltage. All this are DC parameters. Or what I mean to say is, I don't take into consideration of what happened to my circuit with reference to frequency of my input signal. Say I'm giving an input signal of frequency 50 hertz or 50 megahertz, my output will never vary with respect to that. So under that case, that is called a DC analysis. In case if I am trying to make AC analysis, I would like to see what happens to my device or what happens to my circuit. Say I have made an amplifier. How does the gain varies with respect to the frequency variation? When I give 50 hertz, what happened to the gain? When I give 50 megahertz, what happened to the gain? When I move to gigahertz, what happened to the gain? So indirectly, I am trying to see the variations of the gain with respect to the frequency, input frequency. What exactly happens there is when the frequency changes, the frequency associated components like capacitance, inductance will come into picture while the frequency increases or decreases. So those type of analysis is called as the AC analysis. Apart from this, you can have n number of analysis like noise analysis, Monte Carlo analysis, transfer characteristics. One more thing also you will be having what do you call it as a transfer characteristics. A transfer characteristics is the one where you try to plot the variations of output with respect to input. That is, what is the corresponding change in the output with respect to input? This is called transfer characteristics. So whenever I try to plot between input and output, input voltage and output voltage, or input voltage and output current, then that type of analysis is called as the transfer characteristic analysis. That's all. So these are the major analysis which we normally perform. So once you perform this, you could display that in the output screen. In fact, you could see what is the output waveform. You can measure the timing. You can measure the sometime if you want to get the first derivative or second derivative of that also you can get. If you want to find the time delay between 2 points, that also you can make it. So all sort of things could be analyzed. In fact, you can keep on going for this analysis further to get multiple details. Again, as I said, most of the SPICE tool will work with the same protocol, right? You will be seeing that these 3 steps will be the major steps in all the SPICE tool. One such SPICE tool is what I call it as a LT SPICE tool. So let's see how to construct a circuit in the SPICE tool and how to work on this. Right, very simple. The same thing which I have said earlier. Now let's assume that you are new to this tool. You have opened an LT SPICE. First go here and there is a new schematic. So you have opened a new schematic and go to view and make sure that the show grid, this show grid option will facilitate you to construct a circuit so that while drawing the net, it becomes easy for you to align it properly. That's all. So what is the first step I said? You need to construct a circuit. Now our objective is to study the IV characteristics of my N MOSFET, right? The same thing I am showing it for NMOS. You need to do it for a PMOS, and that will be the lab exercise which you need to do. Apart from what I'm showing here, you need to do that separately. Let's see. So first, make a blank untitled one. Of course, you can save this as save as. Go here, save as in the location wherever you want. This is afternoon slot, or what is this slot? A30. I think the slot name is, yeah, L3738. So let's go on with that demo for L3738, right? So this comes as with an extension of ASC. This is a schematic file. Okay, once you save here, now quickly let's see. I want to do an IV characteristics for an NMOS. So first go here. This is the component menu. You can just click over here. So as I said, you have all the components. So you look at the library. This is the place where you have installed your tool. User, admin, documents, LTSpice, 7, lib, symbol. Now you could understand that these are the symbols available. So whenever I select this one, you could see correspondingly the symbol changes. Can you see that? Yes. So what does that mean? So these are the symbols available already in my library. If you want, you can download the symbol file and keep it in your library location under this folder SYM, or the model file should be kept in .lib. That also I will show you. So time being, you could see here the symbols are here. I am going to use NMOS. So NMOS 4 is the symbol which I plan to use. After selecting this, give OK and keep it over here. So this is the NMOS symbol which I am going to use. In order to escape from this, in fact, you can keep it at n number of places. Wherever you click, you will get an NMOS. To get out of this, use escape. Yes. Then I need a voltage source. Again, use this symbol window. Then go to this voltage, select this voltage. So I am going to use a DC voltages. So place it over here, DC voltage. Another one DC voltage can be kept over here. So these are the two voltages which I am planning to give. One is the VGS, my input voltage, and VDS. This is also going to be my input voltage. Let's see what is going to be the current. That's what we are plan is. So the ground is available already here. You can simply pick it up and just connect it at this point, right? Okay, here also I need one ground, so you can keep it as such, right? So whenever I want to put all this component within this pan, you can see here zoom full extent. That will help you to zoom fit in, and this is zoom back or zoom in, zoom out type of option. You can use this. So I'm just using this option. Now directly I don't want to give the voltage to this MOSFET. You know, a MOSFET is a 4-terminal device. This is the gate, this is the source, this is the this is the source, this is the drain, this is the bulk, body, substrate. You can call it by either of these three names. It can be called as bulk or body or substrate. From this you could easily see one thing: the gate is completely isolated from this source and the drain. That's the reason it is called isolated gate, IGFET, field effect transistor. Insulated gate field effect transistor, right? Because you could see there is this area actually in the manufacturing, this will have a silicon dioxide, right? So this will be the gate, and this is source, this is drain, and this is the bulk which you have it, right? I believe now you could understand. If you have any doubt, you can interrupt me. You need not worry, right? I am selecting this resistance. This resistance, you can rotate the resistance by using the option Control R. So you can use Control R to rotate according to your own convenience. And yeah, so let's see here also. I'm just keeping one more resistance. I'm using two resistance. Now let's put that in the fitting window. That's it. Once you have kept all the component, then there is a wiring option. So you could see this red color wire. So once you select this, you get something like a grid here. What you need to do is just put a click over the square point and simply move it. And wherever you want that wire to be connected, just put a single click, right? Like that, you can keep on connecting the circuit as it is wherever you want. Even when you take a bend, you need to click there. Then alone you will get a bend in the right direction. So yes, that's it. But one more point. This bulk, unless you are going to use your, you can short the bulk on the source. In fact, in the theory, we will discuss a lot on that. What is the effect of this bulk on the substrate biasing, things like that. But for most of the digital circuit, the bulk on the source will be shorted. That's what I have done and made that as 0. Once the wiring has been done, you can just get out of this by using an escape button. Right. Now what else is left out? Yeah. Now we need to see first what is the, whenever you take a MOSFET, you need to prescribe its length and the width of it. So I'm just bringing a pointer towards my NMOS, right click, there you can keep the length. I am just giving it as 5U. U means 5 micro. Width I am giving it as 100 micro. You can just change it to any value based upon the need. Now time being, I am giving length to be 5 micron, width to be 100 micron. In fact, you can change according to the library, whichever it is required. Right. So after keeping that, now let us see. So you have kept some value over here. Now this input for the DC, let me fix it as DC voltage to be constant 2 volt. Simply give 2. So this means that this is having a 2 volt. So input voltage, that is between gate and the source, you are given 2 volt. The resistance value I need to give. The resistance I will make it as 1K. 1K. Since the input resistance required is heavy. Towards this resistance, you can keep it as some 100 ohms. That's fine. So I have kept the values of the resistance also now. And this voltage need to be varied. That is, VDS need to be varied. So what I'm trying to do, instead of giving a fixed value, I go for this advanced option. Go to this advanced option. Give a pulse, V pulse. You start with an initial voltage of 0. The maximum it need to go to 10 volt. Delay I'm giving it as 0, time delay. Rise time I'm giving it as 1. Fall time I need not, because it is just going to increase the voltage, so I need not require the fall time also. On time, let me keep it as 1 nanosecond. Period, all those things I will give it as 0. Yeah, these are the setup which I am trying. What I'm trying to say is 10 volt, it is going to rise from the 0 volt to 10 volt. The rise time is 1 second. So within 1 second, you could see the gradually 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. It move like that. Why I want to do that? Because I would like to see the variation in the VDS. This voltage is between drain and the source, because the source point is the common ground over here. Okay, so you have given 2 input voltages, and I would like to measure the current and the voltage across this. I would like to measure the current actually. So let me give something like a label on this point. So to give a label, go to the label, and this label is between drain and the source. So I simply make it as DS, drain source. So bring this label and fix it towards this end. Clear? So this label, why I kept this label is because sometimes I would like to measure the current through this particular point, because IDS I need current with respect to variation in these two. That's why I just kept that value. That's it. Almost a major part is over. Now remember here, the model file for the resistance already it will be available, but only thing for the MOSFET it won't be available. Where can I get the model file for this NMOS? To do this, you can simply go to Google and just you can type PTM model for NMOS. So here, latest model files for PTM. Can you see here? That's it. So this is again, it will be available in the online. Like this, you have model file for, as I said earlier, you can get model files for different devices which you are going to use. In fact, for the same NMOS, PMOS itself, you can have hundreds of models being developed by different universities or fab, right? Now, let me go to the last one, this 180 nanometer BSIM model card for the bulk CMOS. This is version 0.0. If you click this, you will get something like this. Now you could understand predictive technology model. This is what you call it as a PTM, predictive technology model beta version. So this is for 180 nanometer spice, right? Which means that 180 is nothing but the technology node. The length of the MOS transistor is 180. Or the minimum length of the transistor is 180 nanometer. This is for the normal one because you have different variation like the normal or high speed, low speed, like that. But this device model is for normal. Here now you could see dot model NMOS. So you could see level 49 threshold voltage, then LN, L minimum. You could see hundreds of parameters have been kept here in order to describe this behavior. Up to this point, it is for NMOS. So these are the capacitance parameter, these are the voltage parameter, all this. Below this, you will have the model file for uh, PMOS. So can you see here 180 nanometer PMOS spice parameter. So if you are doing the characteristics for a PMOS, you need to take this model parameters. I'm just working on with NMOS, so I have copied only this model parameter. So you simply copy Control C and come back to your designs portion. Go to this .op spice directive and you simply paste here. Control V. Right? Then after doing this, you can just simply copy that and keep it. Now, once you give OK, your mouse will be associated with that. Simply place it over here. So what does this mean is, in the same design area, you have kept what are the details or the models of this particular MOSFET that has been kept here. So if you just want to fit in, you can fit in. You could see these many model parameters are required for this MOSFET. If I want to zoom in, you can zoom in here. Right. That's it. So now the simple what you have done is you have constructed a circuit, you have given the values for all the component, you have given the model file also. Now you need to say what type of analysis you are going to make. So to do this, go to simulate, control panel, simulate, edit, go to simulate. As I said, there are majorly three different way of simulating it. It could be a transient simulation, it could be DC or AC. So go to this edit simulation command. Here perform a transient simulation. Can you see here? This is transient, this is AC, this is DC sweep, noise, DC transfer, DC operating point. But let me go with the transient characteristics. So here what you can do is you can run this for 1 second, right? Once you do this, you get a dot command. Remember, all the spice commands are dot commands. Dot tran 1 means it is running a transient analysis on the circuit for 1 second. That's all. That's it. You have constructed a circuit, you have given the model files, you also said what is the simulation which you would like to perform on this particular device. Now the next thing is only you need to run the simulation. So there is an option to run. Just go to this run option and start clicking this. Once you do that, it will list out. In case if there is an error, you will get an error message. Error in the model file of let me see. So those things can be ignored. Now let's come back to this one, right? Now one thing, remember here, if I to measure the current or the voltage, when I bring the pointer at this point, can you see here the red color arrow is to measure the voltage. This probe, red color probe, is for measuring the voltage. If I want to measure the voltage, say for example, I would like to measure the voltage at this point. You know very well this voltage is going to be 2. So you could see here you get 2 volt. Did you get it? 2 volt. Now if I want to, you could see one more symbol is coming up, not the red one more symbol. This is for measuring the current. If I want to measure the current, then you can measure like this. So if I want to measure the current here, that is the voltage symbol. You could see you will get a current symbol. So if I put it, then that's equal to a current symbol. Are you getting me? So you can measure the current, you can measure the voltage. Only thing is you need to use this probe appropriately. So now again, let me show you properly. You got it? So again, you would like to run this. Okay, you have kept this one. I would like to measure the current. So I am just using this symbol. Now look at here, this is the current. But the x-axis is the time. It is a transient analysis. I would like to make this as a transfer, or what is the current change with respect to different value of VDS. I would like to do that. So to do that, what I'm doing is you just bring the mouse to the x-axis, then right click on that. When you right click on that, you get an details about the horizontal axis. The quantity that is plotted is time. Now I don't want that time, rather I want this to be voltage ds. What is voltage ds? The point where I have kept one marker there, no? I want to measure that voltage with respect to current. So you just give it. Now you could see this voltage keeps on varying. Can you see? Up to 10 volt. The current is varying like this. Or this is VDS versus IDS for a constant value of VGS equal to 2 volt. This is 2 volt. Up to this point it is clear. And if anyone have some doubt, you can just ask your doubt up to this point. Hello. One of you respond. Hello.
No doubts, sir.
No doubts.
Okay, fine. That's all. Now, this is for a single value of this VGS. For a different value of VDS along the x-axis, you get a current flowing from 0, then it comes to saturation. This is what you call it as a device being in different region. So somewhere around 0, there is no current that is cut off. Then after that you get a current. This is what you call it as a linear. Up to this point it is linear. After that the current become almost stable. This is called saturation. Now I think you could understand the device goes through three different region of operation, that is cutoff, linear, saturation. Now I would like to see what is the variation in my input voltage, that is VGS. If I vary this input voltage, what will happen to this current IDS? For the same thing, not for a single fixed value of VGS, I would like to have a varying value of VGS. So let's see how to get that. Now let me go back to the circuit. I would like to make one small change in this. Go here. Instead of giving a fixed value, you use a flower brace V1, close the flower brace. What I mean to say is this is the voltage source, capital V1. You put that in the flower brace. When I keep it in a flower brace, it means that I am going to use this as a variable. Then you keep it like this. So now V1 is the variable parameter. Now I need to tell to which extent it is varying. To mention the variation, go to this .op. I am going to type a single command. This command will enable this V1 voltage to vary over a range. Say dot step space param, PRAM, means dot you vary in step. The parameter is V1. What should be the variation? Let the variation be from 0 to 0 space 10 volt in the span of 2. That's it. So what I'm trying to say, dot step. So vary the step, you sweep the V1 voltage in a step. Which parameter? V1 voltage parameter. What is your starting value? 0. What is your ending value? 10. What is the step value? 2. That's all. So this is just a command. I am just giving that command. Place it just below this. Anywhere, of course, you can keep it in anywhere inside the design space. That's all. So Control S, save. Again, go to simulation again. Go to run. Now close this. Yeah. Now I would like to see what is the current that is flowing across this. Now again, this x-axis need to be varied. Let me pull down this for a while. Yes. Now the x-axis, again, it is a time. So change this as V within bracket. V should be a capital because voltage is shown as in the command as capital V. DS. DS is the note which we have kept there. Yeah. Now you get a list of graph. In fact, you can expand this and see. So along the x-axis, it moved from 0 to 10. Y-axis is my current up to 10 milliamps maximum it gets. So you could see this is for 10, 8, 6, 5, sorry, 10, 8, 6, 4, 2. Less than 2 volt, I don't get. Why? Because below the threshold voltage, you don't get it anything. Or even I have kept, moreover, I have kept the no step size as 2. If I kept as 1, I may get graphs for this also. But below 1, you will not get any output because below 1, the device goes to switch off. You don't get any output. The device is in cutoff region. Or any voltage less than that of, I believe the threshold voltage is 0.9 or something like that. I need to check the model file there. If it is less than that, the device will not get into switch on. Right? Now what you could see here is this is no extended version up to -1. In fact, you can even change that also. The left side you can make it as 0 volt, no issue. Now the graph will again start from this point. That's all. This is a simple IDS versus VDS for different value of VGS graph. So you can just go here for making the report, go here, and you can give it as print previews, things like that, or export. You can use export data as a text that you can do it. You also have some other option. I don't know whether this tool provides that. Save the plot as, let me see. Okay, there is only one. Sometime what happens, you can, I think I need to check it out. You can save that as an image file also. So let me see in the print. Okay, you can save this in either of this option which is available. Yeah, so this is the way you get in. You can even save this print preview. It's a pakka output, we can get it. Right, that's all. The demo for this session is over. If you have any doubt, you can just ask me.